Welcome back, guys. So we've talked about different ways to try to determine a change in entropy as we go through a process. Basically, different ways we can implement the second law. And we said, well, table properties is one. Second law itself is two. If I can quantify this right-hand side, and here's some options. Could be adiabatic, could be heat transfer at a constant temperature, or it could even be reversible. And our third option is what we call Gibbs Equation. So let's see if we can, again, maybe you've seen Gibbs Equation before in chemistry class. Let's see if we can derive this. I've done this derivation a few times. I don't expect you to do a derivation for an engineering course. That's not me. But I know some instructors that do, and that's okay. That's their prerogative. But I do want you to understand how the derivation works. You should have enough math background that when we do a complex derivation that you understand. It's important as an engineer that when you see a simplified expression, that you know where did it come from, what are the rules associated with it, when does it work, when does it not work. In our line of work, if I use a model or an expression that's not appropriate for my situation, we can kill lots of people. It's just how it is. We can literally design things that kill lots of people by accident. So, again, I don't expect you to do derivations personally, but I do expect you to understand derivations. So, I'm going to work through the derivation. It's in your text. I'm going to probably approach it a little bit different than the text does, but hopefully between the two, this helps. So if we look at the first law, let's start there with the first law. Yes, Gibbs equation allows us to kind of quantify parts of the second law, but let's start with the first law. And let's say that I've got, let's just say Q net in, right? Q net in minus W net out is equal to the change in internal energy. We'll say U2 minus U1, big U2 minus big U1, or M delta little u if you like. Okay, so this is delta big U, the total change in internal energy. Heat net in minus the net work out equals change in energy. And again, this is Qn minus Q out minus quantity W out minus Wn. Okay? All right. Or a lot of texts, and I think we've mentioned this in class before, your text likes to put in and out subscripts on heat and work, but a lot of texts will write the first law this way. They'll just say Q minus W equals U. And if we divide by M, if we look at this per unit mass, then that's little q minus little w is equal to little u. Okay? And then let's consider a tiny differential slice of our system. So we just look at a differential size slice, right? Not a whole system. Well, if I just look at a tiny bit of the system, then I'm going to be looking at maybe a tiny amount of heat transfer, a dq if you will, minus a tiny amount of work, dw, is equal to du, a tiny little change in internal energy. All right. Now, if you will recall two things for me. Okay, recall two things for me. First, remember that the work, the boundary work, is equal to the integral of pressure with respect to volume. Or little w then would be equal to the integral of pressure with respect to specific volume, right? Well, if that's the case, then if we just look at a differential amount of work, a tiny little amount of work, that's equal to pressure times a tiny change in specific volume. And that a reversible change in entropy is equal to dq over temperature, right? And if we look at this per unit mass, that means d little s is equal to del little q over t. Or del q is equal to ds times t. Or TDS would probably be the better. TDS is the better way to write that, but I had already written down ds and there wasn't room to put t in front of it. I apologize. So TDS is the better way to write that. And in fact, that's how I'm going to plug it in when we go to the next equation over here. And so page 6, for this set of notes, page 6 says, well, I'm going to plug this TDS and PDV into this expression. So for dq, I'm going to say, well, that's TDS minus PDV is equal to du. Steve, what the heck are we trying to do again? I've forgotten. What are we trying to do? Remember, we're trying to determine delta S. We're trying to find ways of expressing a change in entropy. And we say, well, table properties, the second law, or Gibbs equation. We're trying to figure out Gibbs equation. That's a way to quantify a change in entropy. So let's solve for change in entropy. Change in entropy, of course, is going to be du over T plus, or I'm sorry, plus P dV over T. This is Gibbs free energy equation. Gibbs equation for free energy. This is one version. Now let's write, there's a second flavor of this, if you will, based on enthalpy. Remember, enthalpy, H, is the sum of U and PV. H is U plus PV by definition. Therefore, if I look at a differential slice of H, a tiny little amount of H, take the derivative of H, that's equal to the derivative of this side. Well, the derivative of U is just du. And then a differential size slice of PDV, well, that's a product rule or a chain rule, whichever way you want to look at it. That's PD little v plus V dP. That's how we differentiate this guy. Product rule. Or dH minus V dP is equal to du plus P dV. And if I look at that here, plug this in, so ds I can represent a couple of ways. Du over T plus P dV over T. We had that earlier. And that's also equal to dH over T minus V dP over T. This is Gibbs equation. In its pure, raw, differential form, this is Gibbs equation. Now, how does that help us? Well, again, the whole goal we're trying to do is we're trying to determine delta S. And so what Gibbs equation tells us is that an entropy change can be described based on a change in internal energy and how pressure, temperature, and specific volume relate to each other. And so then we'd say, well, do I have any substances that I can describe how U changes with temperature and how PV and T are related to each other? If I can do that, or H, right, U and or H with respect to temperature, and PDV, how they, P, T, and V, how they all relate to each other. Do we know any substances that we can do that with? Yes, there's ideal gas, right? Ideal gas is kind of the common one. But there's also another set of substances we can do this with. Let's do it first. Let's talk about solids and liquids. It's a little simpler to do solids and liquids first. Okay? So if it's solids and liquids, and let's just look at this form here. Let's not worry about the enthalpy for solids and liquids. Let's just worry about this form here. Now, in our text, a change in internal energy for solids and liquids, we use C sub P. I've got a messenger over there. We use C sub P to describe U values for solids and liquids. Some texts will only use C. They just call it specific heat content. We've already talked about that in our class, why we do C sub P against what our text does. Let's not spend any more time on it. Now, let's talk about this term, right? Well, for solids and liquids, the specific volume doesn't really change much, especially with respect to pressure. Temperature, yes, a little bit, but not a whole lot. There's really not much change for this guy. So for solids and liquids, ds essentially is equal to this du over t, which we can say that's C sub p dt over t, the specific heat times the change in temperature divided by temperature. Okay? Now, still a differential equation. Still, I don't know how helpful that is for us yet. Let's see if we can get this to a helpful form. If I integrate both sides of that equation, integral ds from state 1 to 2 is equal to the integral from state from, and because this is with respect to temperature, this is going to be from T1 to T2, C sub p dt over t. Well, integral ds is just s. So this is going to be S2 minus S1. Hey, change in entropy. That's what we're trying to do. So I can describe the change in entropy is going to equal the integral from T1 to T2 C sub p dt over t. Now here's what we do. We say, well, if I can approximate C sub p, the specific heat, as constant at an average temperature, then I pull the C sub p out of the integral, and then I'm just integrating dt over t. What is the integral of dx over x? Natural log. Right? So this is natural log of, I wrote x, a natural log of t2 minus the natural log of t1. And I'm hoping your calculus instructor is screaming at you that you can simplify that, right? Or an algebra teacher somewhere saying, there's a cool logarithmic rule that lets you simplify that. Difference of the same base log, difference of arguments, you can just take the ratio of the arguments, and that works. For solids and liquids, this is Gibbs equation applied to solids and liquids. We can approximate delta S for solids and liquids just simply knowing the temperature and the specific heat at the average temperature. Okay. Now we also mentioned for ideal gases. Again, this is Gibbs equation. We need to be able to describe how U or H changes as a function of temperature and how P, V, and T relate to each other. Well, we can do that for ideal gases pretty easily, right? du is equal to C sub V dt for an ideal gas. dH is equal to C sub P dt for an ideal gas. And PV is equal to RT, right? Therefore, that means P over T is equal to, R over V. Or V over T is equal to R over P. Okay? Now, why would I do that? Well, let's look. Remember, ds, we said, is du over t plus p dv over t. Let's plug these in. So I'm going to say du is c sub v dt over t. And I've got p over t dv. When I said p over t is r, so this is plus r over v dv. So now, we'll stop there. That's an okay stopping place. It's not ideal. We'll finish out on one last video. Lab Pop here.